Hello everyone, this is Physics 103. This lesson is on atomic structure and on quantum numbers. So our first quantum number is quantum number n. So it tells us about the quantization of energy. So if you would recall from the solution of the hydrogen atom, we have observed that energy is quantized by this quantum number n. So quantum number n is called the principal quantum number. So it tells the quantized energies associated to the hydrogen atom. It ranges from n equals 1 to 3 and so on. So n arises from the radial part of the solution. So as such, a value for n corresponds to sort of a shell. So for example, we have n equals 1, it corresponds to shell k, n equals 2 corresponds to shell l, n equals 3 to m, 4 to n. So you can think of it as a shell defined by a radius. So our next quantum number is quantum number small l. So quantum number L is limited by our first quantum number, which is n. So it ranges from value 0 to n minus 1. So small l quantizes orbital angular momentum, much like how n quantizes the energy. So quantum number L gives a value for our orbital angular momentum L, big L, wherein L as an integer ranges from 0, 1, 2 all the way up to n minus 1. So if we would recall previously, Bohr's model wasn't able to predict the angular momentum properly on the ground state of hydrogen atom. So for the ground state, we have n equals 1. This will give us, from Bohr's model, L equals nh. This will give L equals h bar, which means there is a magnetic moment arising from sort of the orbit of the electron. But experiments show that actually at the ground state, where n equals 1, there is an associated L equals 0. The physical angular momentum should actually be 0, because from experiments result, they observe that there is no magnetic moment. So that is why this successfully predicted the orbital angular momentum, while Bohr failed to predict the orbital angular momentum at the ground state. So the quantum number L arises from the polar part of our radial solution. So it being limited by n, wherein the shells, it is called the subshells. So the subshells are S, P, D, F, G, and H are associated to quantum number L 0, 1, 2, 3, 4, and 5. Okay, so now we have quantum number N and L. So for the last quantum number arising from the solution in Schrodinger's equation, we have the magnetic quantum number, m sub L. So the magnetic quantum number is limited by the values of our orbital angular quantum number. So it ranges from 2 2 times L plus 1 values. So it being just a number, it quantizes the Z component of the R angular momentum, LZ. So the Z component of the angular momentum is given by LZ equals R quantum number M sub L times the factor of H bar. So M sub L ranges from 0 plus minus 1 plus minus 2 all the way to plus minus L. So it arises from the azimuthal part solution of our radial part. Now, M sub L determines the shapes associated with the subshell. So you can also call it as the shapes as the orbital configurations. So for example, we have a subshell L equals 2 or a D subshell. So this D subshell has 2L plus 1 shapes associated to it. So these are, you would recall, L equals 2 gives 5 ml values. These are negative 2, negative 1, 0, 1, and 2. So these numbers determine the shape. So this is for ml equals negative 2. This is ml equals negative 1. This is ml equals 0. This is ml equals negative 1 and this is ml equals negative 2. This is ml equals, she should be 2. ml equals 1. So there we have it, quantum number n, l, and m sub l. So here we have an example. How many distinct states does n equals 3 have? So for n equals 3, we would have values of L from 0, 1, and 2. So for every value of L, for example, L equals 0, we would have 2L plus 1 values for ML. So 2 times 0 plus 1, you would have 1 value. This is only 0. So we have 1 here. For L equals 1, 2 times 2 plus 1, we have 3 values for ML. And for L equals 2, we would have 5 values. So adding them all up, we have a total of 9 values associated to 9 distinct states associated to n equals 3. So each of the 9 states must have the same energy. Now, the 3 quantum numbers n, l, and m, of course, for example, n equals 3 gives 9 quantum states. But there is actually one more missing piece to the puzzle, which is the magnetic spin quantum number. So in the next lesson, we will talk about what is this magnetic spin quantum number.